I just wanted to do a couple little things to help you on this homework. On the first few problems, which kind of give you functions of things, so maybe like number 3 where it says I of t is 3 e to the negative t over 10, this is a pattern matching situation. So remember that the form of this is I of t is I max e to the negative t over rc. So that means that your I max is 3 amps, and that your time constant, tau, is 10 seconds. Okay, so in all of these functions, they either are, if it's like a q of t, like if it's an exponential growth, and that q max 1 minus t over rc, that's the pattern. So again, if you see an equation, of either something times 1 minus t over rc, and then, or something with the exponential decay. If it's decay, that maximum is where it starts. If it's growth, that maximum is that asymptote. So those are just pattern matching ones. So then I think some of the other ones are, reasonably straightforward. There's a little bit of weird calculus, but I think the solutions are helpful. What I wanted to talk through, or maybe where some of my solutions aren't the most helpful, and it might be nice to hear me talk through some of it. So let's look at 13. Okay, so here's the deal. We have this switch. We have R1, and then we have the capacitor, and then here's the ammeter, and boom. Okay, so this was number 13. So that was our capacitor, that was R2. So after a long time, what does that mean? So that's the trick, is you really want to redraw these, okay? So after a long time, the capacitor is charged, right? And if the capacitor is charged, that means that there is a break in the circuit. And so all that really means then is that it's just going to look like this. And there's our ammeter. So it's just going to be 2 resistors in series, right? And so then you've got your very straightforward how you calculate your current coming out of the battery for that. Okay. For number 14, where it says the switch is open, so there's just no capacitor in the circuit. And so it's just this. But remember, we did those sort of equivalent circuit things. And so we want to see that these are in series, and then that's in parallel with that, and then that chunk is in series with that, right? And so in the solutions, I draw it kind of nicer, right? But then you can get that 3 amps. So then the question is, when that 3 amps leaves the battery, right? All of it goes through R1, and then you want to look at this R2 and this R3 plus R4. So the question is, when 3 amps goes in, how does it split up? And then when you realize that this resistor is 5, and then this was like 6 plus 4, so that was 10. So if this has twice the resistance as that, then this is going to get twice the current. And so that's a really nice thing when it has 3 amps going in, because it has to add up to 3 amps, and the other one has to be twice the other one. Okay, so that's how you get that 1 amp and 2 amp going through those 2 branches. And then part C just asks the voltage drop across R4, and you can see that that's in the branch with 1 amp going through, and so it's just a V equals IR thing there. So for part D and E though, now we're going to close the switch. So now let's analyze that. So this is when, it might be nice to redraw. Okay, so we just said that the voltage, right, this was R4, the voltage across R4 was 6 volts. That was in part C. So that means because these guys are in parallel, that the voltage across the capacitor is also 6 volts. Okay, so it's a matter of looking, right? These are at the same potential, these are at the same potential. So they're in parallel, so they have the same voltage. And so then that's a pretty easy way of getting the charge on the capacitor. And then, of course, just the energy, 1/2 CV squared, just a calculation away. So for 15, the initial situation has the switch open and the capacitor is uncharged, okay? Remember that when the capacitor is uncharged, that means that the capacitor will look like a wire. So why don't I redraw that? When we close the switch, then that just makes that a wire. And so your circuit is just like this, right? Where this is, right, that's R1, that's R2, and that's your capacitance. So it's just doing this initially, okay? It is bypassing R2, so it is just doing this, okay? So that's why I2 is 0, and I1 is just your E over R1, okay? All right, but what's really happening here? Okay, it's the moment after that T equals 0, right? There is going to be some current going down here because the charge is building up on the capacitor, which means there's a voltage across the capacitor, which means there's a voltage drop across the resistor, which means there's current in there, okay? So that charge is going to build up, but then after a long time, when the capacitor is full, then it looks like a break. And so it'll just look like R1 and R2. Okay? Right, because this doesn't, right, or open switch is the other way to think about it, a break or an open switch. So that's what's going to happen after a long time, and then you can calculate the current, and then R1 and R2 are in series, so they're going to have the same current, and you get that current with doing that equivalent resistance as well. So then part C is asking what's the charge, okay? And so you see, all right, what is the voltage across that? Well, it's going to be the same voltage that's across R2, because you can see that those are in parallel. Okay, so, and you can calculate what's the voltage across R2, and then you can use Q equals CV to get the charge. And then they like asking about the energy again, and U equals 1/2 CV squared. Okay, so for number 16, Q equals 0 initially, and so we can just redraw that way. And so then that's a nice, easy little circuit, okay? And you can just do your, what's it called? Equivalent resistances. And then after a long time, then that branch goes away, right? Because the the capacitor is fully charged, and so it'll just look like a break in the circuit. Okay, that one was pretty straightforward. 17 is a little bit more fun. So it looks like this with the switch open, right? And if it's been like this for a long time, then those capacitors are charged, right? So if the capacitors are charged, then that's a break in the circuit. And so therefore there's going to be no current flowing. Okay? So you can kind of redraw this like because if there's no current flowing, then there's no voltage drop across the resistors, right? So if there's no voltage drop across the resistors, then that means the full voltage drop is across the capacitor. So that's why we can just redraw it like that. So VC1 equals VC2 equals that full EMF. Okay? Part C, it's kind of fun. So when you redraw this, but now we have the switch closed, then let's pick a different color. These are still breaks because they're fully charged still. So that means that that is our new circuit. And so it'll just flow through those resistors. So that's, hopefully at this point you're seeing the benefit of redrawing these things. All right, so for part D, it asks, about the voltage across the capacitors, and then you can get the charge and energy stored. So then, why not just redraw this one more time. Oh, that's a resistor. And let's get yet another color. How about green? Okay, so these are charged capacitors, right? So they have a voltage across them. And hopefully, by looking at those points, you see that the voltage across that is equal to the voltage across that, and the voltage across that is equal to the voltage across that. So, because you know the current that you just figured out in part C, you should be able to know the voltage by doing V equals IR, and then you can relate that to the capacitor voltage. Okay, so number 18 kind of looks like this. That's whatever EMF that is, 12 volts. Who cares, whatever. The point is that there's something interesting going on in the other part. So hopefully at this point you're looking at these and you're saying, okay, if my capacitor is uncharged, then it's going to look like a wire, and like if it was like this case, if it was uncharged, it would bypass the 6 ohm because it would rather go through the capacitor. In this case though, there's no switch, right? So this is like that long time thing. So you can definitely assume that the capacitor is charged here. So if the capacitor is charged, then that means that it's a break. Okay, which means that it goes through the 4 and the 6. And then you have a 4 and a 6, which is 10, and then 10 and 10 in parallel, and then the 3. So that's just a pretty straightforward part of a problem there. And so, later when it asks about the voltage across the capacitor, you say, oh, it's the same voltage as across this 6 ohm. And so those calculations end up being reasonably straightforward after that. Okay, so number 19. So initially the switches are open and the capacitors are uncharged. That's what they say. So if the capacitors are uncharged, you'd say, oh, cool, those are like wires, except because with those switches open, there's no possible path for any charges, so we just have no current. All right, so now it switches on just S1. So now this is a nice little simple RC circuit, and that one should be pretty straightforward because after equilibrium is reached after a long time, the full potential of the battery is across the capacitor. So part A is pretty easy. But now switch S1 is opened and switch S2 is closed. So now this is charged and this is uncharged. So now you have a certain amount of charge on Q1, and then afterwards it's going to spread out so that Q1 has to equal, the after charges. You have to, be able to add them up. so, because there's nowhere else for charges to come from or go to, so that the charge has to be conserved, okay? And so what's going to be sort of that end result is that the potential across that capacitor has to equal the potential across the other capacitor. So that's just some algebra, honestly. And then for fun, they're like, you know what? Now that, right, these two have some charge on them, right? So this has some Q1 prime, this has some Q2 prime. Now, for fun, let's put the battery back in. Okay, so now the question is, what will happen? Well, now the battery has that EMF, that voltage across it of the EMF. So that means that these have to also have that voltage of EMF across it. Okay, so it's going to give you some more charge so that those can satisfy, right? So, okay, that's double prime now. C1e and Q2 double prime is C2e. Hopefully that makes sense. Take a little bit to just think about. I just wanted to talk about the big ideas here. So, okay, but for 21, part A, pretty straightforward. It's just that the capacitor has the exact same voltage as the battery, so you get your Q equals CV stuff going. What happens when we open that? We open that, so this is now charged. And then we close S2. And it might even be useful just to really make it clear that this resistor, that the bottom of this resistor is at the same potential as the bottom of C1. And so that might help to think about that. So this one initially is uncharged. So when this switch is closed, we connect them, then the voltage from C1, right, was E before, right? That was from part A. So that's the voltage that it has on it. So that means that this to this is also E. But if this is uncharged, then that initial current that goes through there is just E over R, okay? Because there's no voltage on across C2 at that initial point, okay? However, once it comes to equilibrium, then the current's gone, and then VC1 equals VC2, okay? Now that VC1 and VC2 are not necessarily E now, right? But what must be true is Q before equals Q after. And then that's just some annoying math, but it's not so bad. And then it asks about the total energy, and there it's going to be easier. You have the charges to do a Q squared over 2C and you just add those up. 22, the only thing that might be, I mean, it's all, I guess, a little bit weird, but you're pulling these capacitor plates apart, so you're doing work, right, to increase the energy in it. And the trick there is to recognize that because you're doing it really, really quickly, and it says the time is very short compared to the time constant of the circuit. That time constant of the circuit, RC, tells you how fast that capacitor is going to be charging up. And so, or discharging, depending on the circuit. So in this case, you can assume that the charge, that the capacitor's charge won't change in the amount of time that it takes for you to pull apart those things. So that's the idea there. And finally, 23. It's kind of like a weird Wheatstone bridge, But the trick is to recognize that you have the same current going through your resistors, that you have the same charge on your capacitors because they're in series, and then of course recognizing that this potential and this potential have to be the same if VAB is 0, then those are at the same potential, that's at the same potential. So the potential across this is the same, and potential across this and potential across this is the same. So hopefully this helps with some of it. I told you it was brutal.